In this video, we want to talk about a shortcut for finding a second primitive cube root of unity in finite fields. That is, given a first primitive cube root of unity, we can find the second one. So let's take a look at a couple of examples. And before we get to the shortcut, let's see how we might otherwise do this. So let's say we're in the field F19, and we know that one of the primitive cube roots of unity is 7. Well, since we know that 7 as a primitive cube root of unity generates all the other cube roots of unity, then we can just look at the set that 7 generates. Namely, 7 and 7 squared would be 49, 7 to the third power would be 343. And if we simplify that by doing the operation modulo 19, we get 7, 11, and 1. So these are our three cube roots of unity, and these two are indeed primitive cube roots of unity. So the answer would have been 11. But that took a while. So that's why we want to have a shortcut. But let's look at one more example to convince us of how much work it would be to indeed always use this method. So what we ended up doing here was taking 7 squared, right? So if we take a look at this example here, and we know that 95 is a primitive cube root of unity, then what we would need to do is square 95, which would be 9,025, and then we would have to divide that by 1,303 in order to find out the remainder, and that goes in 6 times, so 1878. This is 0, 7, and a 12. So we see that that indeed would be the other primitive cube root of unity. But there is a faster way. Namely, if we write these second cube roots of unity that we found as negative numbers, a pattern emerges. So 11 in F19 is the same as negative 8. And 1207 in F1303 is also negative 96, right? These are the same things. So you see the pattern? 7 plus 1 is 8, and then flipped about 0 gives us negative 8. 95 plus 1 is 96, and then flipped about 0 is negative 96. So, how would we find the answer here? Well, of course, we just take 10 plus 1 and flip it. We add 1 and flip it. So we get negative 11. Indeed, we do not even need to know which field we're dealing with. 46 gives us negative 47. 45 gives us negative 46. 365 gives us negative 366. So that's pretty quick in comparison to having to do all this multiplication and then division. But how can we be sure that this is a real trick and doesn't just work for these cases? Well, let's prove it. So here's my claim. My claim is that given a primitive cube root of unity A, then B, which we'll define as being A plus 1 flipped about 0, is also a primitive cube root of unity. So let's prove that. Actually, let's rewrite what I'm claiming. So A cubed is equal to 1. And A squared is not equal to 1. And A itself is not equal to 1, right? That's just the definition of primitive cube root of unity. And what I want to show is that b cubed is 1, and b squared is not equal to 1, and b itself is not equal to 1. So, now we can prove it. Let's raise b to the third power and see what we get. In other words, first we want to just show that b is a cube root of unity, and afterwards we'll show whether it is a primitive cube root of unity. So b to the third is just going to be negative a plus 1, all of this cubed. And if we multiply that out, we get negative a to the third minus 3a squared minus 3a minus 1. At this point, we can sub in for the a to the third because we know that that's equal to 1. So we end up with a negative 1 there. So that gives us negative 3a squared minus 3a minus 2. Although it looks so nice here that I have negative 3 and a negative 3 and almost a negative 3, I'm going to write a negative 3 there and then just add 1. So I can indeed factor out my negative 3, which gives me a squared plus a plus 1, and then at the end we have a plus 1. And now comes the big moment when the clever thing happens. I'm going to rewrite this here as a to the third minus 1 divided by a minus 1. So if you divide that out, indeed, you will get this as a quotient. But we do need to make sure that this division is defined, right? So we need to know that a minus 1 cannot be 0. But since we know that a is not equal to 1, we also know a minus 1 is not equal to 0. And we also need to check that a minus 1 has an inverse. But since we are dealing with a field, every non-zero element has an inverse, so this division is indeed defined. And at this point, we need to remember to write in this 1 because the rest of this is going to vanish. Because a to the third minus 1, as we know from our assumption, is indeed equal to 0. So all that goes to 0, and we have our proof that b is indeed a cube root of unity. Now we need to prove that b squared is not equal to 1 and that b is not equal to 1. So let's assume for a moment. Assume b is equal to 1. Well, that would imply that negative a plus 1 would be equal to 1. Right? That's just the definition of b. And that would imply that a is equal to negative 2. Now, we'll come back to that in a moment. Let's look at the other case. Let's assume that b squared is equal to 1. So b squared being equal to 1 would imply, if we multiply both sides by b to the third is equal to b. But we know that b to the third is equal to 1, right? We just proved that. And that implies, of course, that b is equal to 1. And we just saw that if we assume p is equal to 1, then we end up with a being equal to negative 2. So let's assume that a is equal to negative 2. What we want to do now is show that that leads to a contradiction. And all of this will be gone. So, if a is indeed equal to negative 2, then that would imply that a to the third would be equal to negative 8. But we already know that a to the third is equal to 1. So if we add 8 to both sides of this equation, we end up with 0 being equal to 9, which of course for any infinite field would already be a contradiction, but since we are dealing with finite fields, it could be the case if we're operating, for example, modulo 9. So that would mean that the characteristic of our field, in other words, the number of times that we have to add 1 to itself in order to get 0, would be 9. But that cannot be the case because all finite fields have a prime characteristic. So the only other thing that could happen is that we would be dealing with characteristic 3. Right? So if we were dealing modulo 3, 0 would also be equal to 9. So let's assume for a moment that we are operating with modulo 3. Then that would mean that q being the number of elements in the field, would be equal to 3 to some power. But now we need to remember under what circumstances we have a primitive cube root of unity. So we have a primitive cube root of unity when 3, because we're dealing with cubes, divides q minus 1. So let's see if that could work with the characteristic of 3. So 3 divides 3 to the k minus 1. Could that be? No, that won't work because 3 divides 3 to the k, and 3 does not divide negative 1. So we have our contradiction, which means a cannot be equal to negative 2, which means that b cannot be equal to 1, and b squared cannot be equal to 1. In other words, b is a primitive cube root of unity, exactly as we wanted to prove. So if we look back over this proof, we might notice that although we've just been talking about these prime order fields, that we did indeed take care to observe the case that it's possible that we could have prime power order of a field. So this theorem should also work for fields like f4, right? 2 squared. So let's take a look at that. If we are dealing with this field, and for some reason we know that x is a primitive cube root of unity, then we need only add 1 and flip it about 0 to get the other one. And of course, since we're dealing with a characteristic of 2 here, in other words that we can only have coefficients of 0 or 1, then this negative sign just as well may be a positive sign, and we have our answer. X plus 1 is the other primitive cube root of unity. And if we're dealing with this field here, f16, then x squared plus x is our primitive cube root of unity. We add 1, and we add a negative sign. And again, because of the characteristic here, we can just ignore that negative sign, and we have our answer. X squared plus x plus 1. So to check these answers, obviously, we would just have to multiply x plus 1 to the third power, and then divide by this irreducible polynomial here, and indeed the remainder that we would get would be equal to 1. Same goes for this case when we divided by this irreducible polynomial. Now if we look back over our proof one last time, we notice that we never actually made use of the assumption that we're dealing with a finite field. That is, our theorem should also work for infinite fields. for example, the complex numbers. So we have here the famous unit circle with the 3 cube roots of unity forming a triangle. And if we take one of those cube roots of unity and write it down, add 1, and flip it, we end up with negative 1/2 minus the square root of 3 over 2i, which, of course, is exactly what we would expect to get, since that is indeed the other primitive cube root of unity. Now you might ask yourself, well, does this work for all fields? Well, we made no assumptions in our proof that refer to any special fields, so this would also work for a field like R. But here's the rub. R has no primitive cube roots of unity. If we have an A such that A cubed is equal to 1, then that implies that A is equal to 1. So there are no cube roots, no primitive cube roots of unity in R. If there were, then the theorem would tell you how to find the other one, but there are none. So it is vacuously true, just as it is vacuously true in Q or, for example, F5, because in F5, 3 does not divide Q minus 1, so 5 minus 1 in this case. So since there are no primitive cube roots of unity, the theorem holds vacuously. The theorem does hold, for example, in the complex numbers and in the prime order fields, for example, F7 or something like F2 to the 4, in a helpful way this time, right? Where we can find that other cube root very quickly. So we see it holds in all fields, sometimes vacuously, sometimes helpfully. So now you have a shortcut for finding a second primitive cube root of unity in all fields.